Welcome back to the channel. This is AI Academy, and today we're diving into one of the most revolutionary concepts in AI, Generative Adversarial Networks, or GANs. What if I told you that AI can create things that look and feel completely real, like faces, artwork, and even voices? That's the power of GANs. In the next 15 minutes, we'll explore how GANs work, why they're game-changing, and how you can start building your own. So grab your coffee, hit that subscribe button, and let's get started. Imagine two AI systems locked in an eternal battle. One is trying to create perfect forgeries, while the other is trying to catch those forgeries. This is the essence of GANs. Think of it like this. You have a master counterfeiter who's trying to create fake paintings that look exactly like Van Gogh's work. On the other side, you have an art detective whose job is to spot the fakes. The counterfeiter gets better at making fakes, so the detective gets better at spotting them. The detective gets better at spotting fakes, so the counterfeiter has to improve their technique. This back-and-forth competition drives both to become incredibly good at what they do. In GAN terms, the counterfeiter is called the generator and the detective is the discriminator. And just like our analogy, they make each other better through competition. Let's break down the architecture. A GAN consists of two neural networks competing against each other. First, we have the generator. Its job is simple: create fake data that's so good it can fool anyone. It starts with random noise, just mathematical gibberish, and transforms it into something meaningful, like an image, text, or music. Think of it as a magical paintbrush that turns random dots into masterpieces. Then we have the discriminator, the critic. It looks at data and makes a binary decision. Is this real or fake? It's trained on real examples, so it knows what authentic data should look like. The genius is in how they're trained together. The generator tries to fool the discriminator, while the discriminator tries not to be fooled. It's like a never-ending game of cat and mouse. Here's where the magic happens, the training loop. Let me walk you through this step by step. Step 1, the generator creates fake data from random noise. Step 2, we mix this fake data with real data and feed both to the discriminator. Step 3, the discriminator tries to classify each piece as real or fake. Step 4, we calculate how well each network performed. Step 5, we update both networks based on their mistakes. Initially, the generator produces garbage and the discriminator easily spots fakes. But as they train together, the generator gets incredibly good at creating realistic data and the discriminator becomes an expert critic. The beautiful thing is when training is complete, we can throw away the discriminator and use the generator to create unlimited new realistic data. Now let's talk about the mathematical heart of GANs, the min-max game. Don't worry, I'll keep this visual and intuitive. GANs are based on a min-max game. The generator wants to minimize the discriminator's ability to tell fake from real, while the discriminator wants to maximize its detection accuracy. Mathematically, this creates a beautiful equilibrium. When both networks reach their optimal state, we achieve what's called Nash equilibrium. Neither can improve without the other getting worse. Generator loss. How well did I fool the discriminator? Discriminator loss. How well did I distinguish real from fake? During training, you'll see these losses dance around each other. Sometimes the generator is winning, sometimes the discriminator. The sweet spot is when they balance out. All right, let's get our hands dirty with some actual code. I'll show you how to build a simple GAN in PyTorch. First, let's define our generator network. Next, our discriminator. And here's the training magic. As you can see, it's surprisingly straightforward. The key is in the adversarial training where both networks improve together. GANs have evolved tremendously since 2014. Let me show you the major variants. Vanilla GANs are the original. simple but effective for basic tasks like generating handwritten digits. Conditional GANs, or CGANs, let you control what you generate. Want a cat? Just tell it cat. Want a dog? Say dog. It's like having a genie that follows your creative commands. DCGANs brought convolutional layers to the party, making image generation dramatically better. These are behind many of the stunning face generations you see online. LapGANs create ultra-high-resolution images by building them up layer by layer, like a digital artist adding more and more detail. And SRGANs can take a blurry, low-resolution image and enhance it to incredible detail. It's like CSI Enhance, but real. GANs aren't just academic toys. They're reshaping entire industries. In creative arts, GANs are generating paintings that sell for thousands of dollars, composing music, and even writing poetry. In entertainment, they're creating realistic visual effects, and yes, deepfakes, though we need to be mindful of the ethical implications. In healthcare, GANs are generating synthetic medical data for training, enhancing medical imaging, and even discovering new drugs. Fashion designers use GANs to create new clothing designs, and architects use them to generate building layouts. For machine learning practitioners, GANs are incredible for data augmentation, creating more training data when you don't have enough. Why are GANs so revolutionary? Let me count the ways. First, the quality is unmatched. GANs produce incredibly realistic synthetic data that's often indistinguishable from real data. Second, versatility. GANs work with images, text, audio, video, you name it. They're the Swiss Army knife of generative AI. Third, they're mostly unsupervised. You don't need labeled data for basic GANs, which is huge when labeled data is expensive or rare. Fourth, creative potential. GANs don't just copy, they create entirely new, novel content that never existed before. But let's be real, GANs aren't perfect. They come with significant challenges. Mode collapse is a big one. Sometimes the generator gets lazy and only learns to create one type of output. Imagine asking for different dog breeds, but only getting golden retrievers. Training instability is another headache. The adversarial training can be like balancing on a tightrope. One wrong step and everything falls apart. They're computationally expensive. Training a good GAN requires serious hardware and lots of time. Evaluation is tricky too. How do you measure creativity or realism objectively? Unlike traditional ML where accuracy is clear, GAN evaluation is more art than science. And we can't ignore the ethical concerns. Deepfakes, misinformation, copyright issues. With great power comes great responsibility. GANs represent one of the most exciting frontiers in AI. We've covered a lot today, from the basic adversarial concept to real-world applications and challenges. In just under a decade, GANs have gone from generating blurry 32 by 32 images to creating photorealistic faces, artwork, and even videos. The progress is absolutely mind-blowing. Looking ahead, GANs will likely play crucial roles in virtual reality, personalized content creation, scientific discovery, and applications we haven't even imagined yet. Your turn now. Start with the simple PyTorch example I showed you. Experiment with different architectures, try different datasets, and, most importantly, have fun creating. If this video helped you understand GANs, smash that like button and subscribe for more AI deep dives. Drop a comment below with what you'd like to see generated by GANs. I read every single one. Next week, we're diving into transformers and attention mechanisms, the technology behind ChatGPT and GPT-4. You won't want to miss it. Links to code, papers, and additional resources are in the description below. Until next time, keep learning and keep creating.